So today we're going to discuss section 12.6, which involves Lewis structures. So a Lewis structure is a way to represent an element showing how things are bonded, but we're just going to involve valence electrons. Okay, valence electrons are those outside electrons. In ionic bonds, valence electrons are stolen. In covalent bonds and polar covalent bonds, valence electrons are shared, either equally or unequally. So a Lewis structure is a representation of a molecule that shows how the valence electrons are arranged among the atoms. So it shows how those electrons are used. The most important requirement for any molecule is that the atoms achieve noble gas electron configuration. And we talked about this in section 4 and 5 configuration. And that's going to apply to Lewis structures. To represent the electrons, we're going to use dots. Really creative, I know. And only valence electrons are going to be used. An easy way to figure out valence electrons is to look at group numbers. So if you look at our little drawing up here, here are the valence electrons for elements except transition metals, and you can see that it's the same for the entire group, which is the vertical. Okay, so let's look at some Lewis structures for different types of compounds involving different types of bonds. Okay, for ionic compounds, let's look at KBr. So, potassium, we need to find the valence electrons. Potassium has 1, because it's in that first group, and bromine has 7. So that's a total of 8 valence electrons, or 8 dots. Well, ionic bonds are a little different. Because the electron from potassium is stolen, right? So there's my 7 for boron, here's my 1 from potassium. It gets stolen. And so what really happens is K forms a +1 ion, and then bromine has all 8 of these electrons, and it's a -1. And anytime we have a charge, it gets a bracket. And we'll look at that more. Ionic compounds, we don't normally draw Lewis structures, so let's get into what we normally use, which are covalent compounds. Couple rules you need to follow. First is the duet rule. This says that hydrogen forms stable molecules when it shares 2 electrons. Because if you look at where hydrogen is, it only needs to take on 1 more electron to be like helium, which is its noble gas electron configuration. So hydrogen is a little bit different than pretty much all the rest. The octet rule applies to second row nonmetals, or the second period. And this means that they require 8 valence electrons to fill the outer shell. Okay, so if you remember from the Bohr model, 8 electrons filled that outer shell, and nonmetals are going to take on electrons in order to get noble gas electron configuration. We can have 2 types of electron pairs. We can have bonding pairs, which are shared between elements. We indicate those with a line. Or we can have lone pairs, which are unshared pairs of electrons, and we indicate those with 2 dots. And we will look at the difference. Something else to remember is that noble gases do not form bonds because they already have a full outer shell. And so they don't need to form bonds with anything. And like we talked about before, the group numbers represent the number of valence electrons, and we don't use this for transition metals because we're only looking at covalent compounds, which are 2 nonmetals. So let's look at the steps for writing Lewis structures. First, we want to include all valence electrons from all atoms involved in the compound. Bonded atoms are going to share 1 or more pairs of electrons. Because they have to be bonded in some way, it at least requires 1 pair. That would be 2 electrons. Each atom needs enough electrons to complete its outer shell. Remember, it wants to have that noble gas electron configuration. This means 2 for hydrogen, or 8 for the second row nonmetals. And this actually applies to most other nonmetals with a few exceptions. Make sure that the octet rule is satisfied, or the duet rule for hydrogen. That's going to help you double check your answer. And remember also that valence electrons belong to the molecule as a whole, not to any one particular atom. Even if 5 valence electrons come from nitrogen, that doesn't mean that those 5 belong to nitrogen. They're being shared within the whole molecule. Okay, let's look at an example then. Let's write the Lewis structure for water. Okay, so we have H2O. It involves hydrogen and oxygen. Each hydrogen, if I look at my periodic table, is in that first group, so it's going to donate 1 valence electron. But there are 2 hydrogens in water, so that's 2 valence electrons from hydrogen. Oxygen, if I look at my periodic table, is 1, 2, 3, 4, 5, 6th group. I'm not counting transition metals, so there are 6 valence electrons. There's only one oxygen, so that's 6. So I get a total of 8 valence electrons. So I'm going to put oxygen in the center because it's the only one. I want to try to make my compounds as even as possible. And so that means I'm going to put a hydrogen on each side. Hydrogen will never be in between two things because hydrogen only wants 2 electrons. And this means one bond. So it'll never be in between. It's always going to be on the outside somewhere. So now what I want to do, and there are lots of different ways that you can do Lewis structures. I like to give everything single bonds and give everything what it needs to be stable and then count them up and compare to my total. So we're going to do that. Okay, so I'm going to bond hydrogen to oxygen here, and I'm going to bond hydrogen to oxygen. So what this means is that there are actually 2 electrons being shared, and since hydrogen is able to share those 2 electrons, it's satisfied. Same thing with this one. So this hydrogen, the duet rule, is also satisfied. Oxygen needs 8 to be stable. Right now it's sharing 1, 2, 3, 4. So I'm going to put 5, 6, 7, 8. And so now oxygen has 8 valence electrons that it's sharing, and so its octet rule is satisfied. So now I'm going to count up. I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 valence electrons used. I had 8 available. So this is my Lewis structure. Okay, let's look at another example. CF4. Carbon is group 4, so it's 4 valence electrons. Each fluorine donates 7 times 4, which is 28, plus the 4 is a total of 32. Carbon, there's only one of them, so I'm assuming it's going to go in the middle. And as you could see from oxygen, I had kind of 4 bonding sites, so that's where we're going to put our 4 fluorines. So 1, 2, 3, 4. Carbon is now sharing 2, 4, 6, 8, so carbon's octet rule is satisfied. Now let's do fluorine. We have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Because remember, none of these are hydrogen, so that we want to satisfy the octet rule. Now let's count up how many we used. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I had 32 available, so I'm good. Okay, not everything is going to have some single bonds, and so we need to look at molecules with double bonds or more, multiple bonds. Okay, so you do the same thing. You count up the total number of valence electrons available. But what's going to happen is when we do what we did before, where we gave everything, tried to satisfy the octet rule, it's not going to work out with the number of electrons that we're given. And so what this means is that we're going to need the atoms within the molecule to share more than one pair of electrons. So we're going to need more than one single bond. And we just established this kind of through trial and error. There are 3 types of bonds. There's the single bond, which is 1 electron pair, which is a single line. There's the double bond, which is 2 electron pairs, or 4 electrons total. That's 2 lines. Or there's a triple bond, which is 3 electron pairs, or 6 electrons total. And that's 3 lines, because it's 1 line per pair. So let's look at an example. Let's do C2H2. Well, carbon is 4 valence electrons, but there's 2 of them, so that's 8 total. Hydrogen donates 1 valence electron. There's 2 of them, so that's 2 total. So I have 10 valence electrons to work with. Now, this is a little tricky, and this is an organic compound. So anything like this that you're not familiar with, I'll make sure to show you how it bonds. But this is how C2H2 bonds. So hydrogen is sharing a pair here and sharing a pair here, and so I know those are satisfied, stable. And so now carbon wants 8. It's right now sharing 2, 4. So I'm going to do 6, 8, and the same thing on that carbon. So now let's add up. I have 2, 4, 6, 8, 10, 12, 14. I have too many. So what that means I'm going to need to do then is share more than one pair. So what I'm going to do is take this pair, take this pair and this pair, and instead of them being separate, I'm going to make carbon share another pair. So I'm going to put a double bond right there. Now let's count. We have 2, 4, 6, 8, 10, 12. Still too many. So I need my eraser again. Well, I have this lone pair on carbon and this lone pair on carbon. So instead of them each having their own, I'm going to erase those and make them share a third pair. So now let's count. So I have 2, 4, 6, 8, 10. And I need a 10, so that works. Let's check check that I satisfied all my rules. Hydrogen has 2, so it's satisfied. This hydrogen has 2, so it's satisfied. This carbon is sharing 2, 4, 6, 8, so it's satisfied. And this carbon is sharing 2, 4, 6, 8, so it's satisfied. So H, single bond, carbon, triple bond, carbon, single bond, hydrogen. That works for my Lewis structure. Okay, I can also have what's called resonance. This occurs when you can draw more than one Lewis structure. So let's do carbon dioxide. Carbon is going to donate 4 valence electrons. Each oxygen donates 6 times 2, which is 12, so that gives me a total of 16. Because carbon is the only single one, I'm going to put it in the center. I'm going to single bond everything first and satisfy everything's octet rule, and then compare that to my 16. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many. That means I need to do double bonds. I'm going to erase this pair and have them share right there. 2, 4, 6, 8, 10, 12, 14, 16, 18. Still too many. So I think I'm going to, let's see, I'll take this one and make them share. And we'll do that. So 2, 4, 6, 8, 10, 12, 14, 16. That works. But that's not the only structure I can draw. I can also do this. Because if I look, I have 2, 4, 6, 8, 10, 12, 14, 16. So I have a total of 16. This oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. And this oxygen has 3 lone pairs and a single bond, which also make it 8. So both of these will actually work. Okay, and so when you're looking at resonance, you may need to draw more than one structure if that's what it asks you to do. So you can only have resonance when you have double or triple bonds present, so always be looking for that. Okay, so let's look at how to do the Lewis structure for ions. So when we do ions, we need to make sure to either add or subtract the electrons based on the charge. And we would include brackets just like we did at the beginning for the ionic compound. So let's look at an example. Let's look at SO4. Oh, let me get a pen here. Okay, so sulfur donates 6 valence electrons. Oxygen donates 6, but there's 4, so that's 24. And then we have this minus 2. Well, since we're adding up electrons, we're actually going to add 2 more to our total. If this was a 2 plus, we would be subtracting 2 because this means that 2 electrons got removed because it's positively charged. Okay, but we have a minus 2, so this is 32 total. Since sulfur is just by itself, we're going to put it in the middle for oxygen, so we're going to bond them each with single bonds to start. Let's satisfy everything's octet rule. Okay, so now each item has 8 electrons, and that's what they all want to be stable. Let's count up. So starting here, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that matches. Last thing we need to do is, because it's an ion, and I always forget to do this, brackets with the charge. Okay, so similar, just got to remember that little tiny extra step. Alright, there are some exceptions to the octet rule. Boron only wants 6 electrons instead of 8, so we say that it's electron deficient. Beryllium can also be electron deficient. And traditionally, any molecule that contains an odd number of electrons won't really conform to Lewis structure rules, so if you're ever adding them up and you get an odd number, you probably did something wrong, so go back and recheck it. The valence electrons. Also, some elements below period 2 can have what are called expanded octets, which means that they will hold more than 8 electrons. And so we can have S8, which has a sulfur in the center and then a whole bunch around it, and it's got way more than 4 bonds. Okay, so here's some practice, and we'll do some more examples in class. Have a good day.